Hi, my name is Mouton. I'm the group reporter for Group 3. And today I'm going to be talking about the gas turbine experiment and just going over the results of it. First, we're going to go through the objectives, what we're supposed to be doing and how we're supposed to be collecting our data. We'll go through the apparatus and what makes this thing work. We're going to talk about how we actually collected the data and where we stored it, and how I analyze this data to come to my final conclusions. The objectives of this experiment are to understand the overall principles and operating procedures of this gas turbine, and also to report our temperatures, pressures, and thrust values, and that way we can perform calculations to quantify the overall efficiency and performance of our gas turbine. So the gas turbine itself is composed of a compressor, combustion chamber, a turbine, and a nozzle. What happens is gas enters the compressor here, and this high pressure gas comes into the combustion chamber where it mixes with our fuel and ignites. It comes down and the air expands through the turbine, which in turn powers our compressor, and then is exhausted outside through the conversion nozzle. The actual Brandon cycle for this, right here we have from the compressor, we have gas going through the compressor, which is our isentropic process. And we have an isothermic process whenever it goes through the combustor and heat is added to the system after igniting. Then we have the gas coming back through the turbine, expanding, and then being ejected through the nozzle. And the overall theory is that our efficiency will increase as the pressure ratio increases. How I analyze my data: to calculate the mass flow rate, which is the most important thing we need for everything else, I use the first law of thermodynamics. And after that, the exit velocity is calculated using the formula that was given in our manual. And then I calculated the fraction of energy released in the combustion chamber and the nozzle. Moving on to my actual data, what I did was I calculated all these values for all the data given. We didn't perform the procedure this week because the gas turbine's out of commission over here. So I used all the data showing how precise this machine actually is over time. There's over 100 trials, and you can still see that right here we have the old collected data, and in red the factory results. And while the data is off, if you look at the trend line, you can see how similar the slopes actually are, showing that the mass flow rate will increase as the RPMs increase. And the RPMs we took between 40,000 and 80,000. Onto the velocity versus RPM. Between 40,000 and 50,000, you see a slight pickup. My understanding is that this is because the machine is just getting started, pretty much imagine warming up, and there's just a slight irregularity at the beginning. But as you can see, after 60,000, the slope is similar to our factory results. And so at the bottom, you can see my mean value and standard deviations for all these calculations. Onto the fraction of fuel burned in the nozzle. This is what I thought was interesting. It shows that we have an increase in the fraction of fuel burned at the nozzle from 40,000 to 60,000, then again it drops off. Unlike what I expected it to rise as the RPMs rose, showing that just because the high temperature and high pressure coming out of that nozzle, I expected more fuel to be being burned. Onto the fraction of energy released in the combustor. Again, I think my calculations, I know my calculations are off. I have fractions over 1. I can't really understand why this is happening. When we perform the experiment, I might have some more insight as to why these calculations are wrong. But the factory result is what I expected. As the RPMs increase, we're getting closer to 100% efficiency in the combustion. And then finally, our thrust versus RPMs. This is as expected again, that our thrust will increase as rotations per minute increase, and our collected data is in agreement with our factory results, which is slightly off again. Now the isentropic efficiency of the compressor. Here are my equations that I used to calculate. I found my theoretical temperature output first, and then plugged it into my efficiency calculation. And here's a little small selection of the data showing that as RPMs increase, the efficiency drops. And here's the actual plot for it. And what I understood this is that as the compressor is having higher load put onto it, it's not going to perform as well, because as the engine is running faster, there's more air being pushed through. Then finally onto compressor and turbine work. We have the same values at every RPM, just for the negative sign. Again, as I said, it's the turbine that's driving the compressor, so work in equals work out, which makes sense here. Final conclusion, my temperature, final experiment temperature 4 without the experiment, which wasn't showing the factory results, which I found odd. I chalked this up to just the fact that as the smaller we're working with, the temperature being expelled, it's a high pressure situation and a high speed, and that could possibly be why we have a higher temperature there. We looked at the brightness cycle, we looked at calculations we used back in thermo that I hadn't used in forever. And one of the biggest things I learned from this experiment is how important it actually is to do the procedure and not just have the data, because some of the things that were off for us, I couldn't tell why, and I had no explanation because I hadn't actually looked at the machine. With that, I'm going to close, and if anyone has any questions.